Hello everyone, I am Kazuya Kakizaki from Japan. I will present our work, Certified Defense for Content-Based Image Retrieval. Content-Based Image Retrieval CBIR is a task to retrieve visually similar images. Given query image and candidate images, CBIR ranks candidate images with Euclidean distance between features calculated by deep neural networks. Unfortunately, CBIR is known to be vulnerable to adversarial attacks. Figure shows overview of adversarial attacks against CBIR. Adversary modifies ranking results by perturbing input called adversary examples. When query image is an adversary example, adversary attack is called query attack. When some candidate images are adversary examples, adversary attack is called candidate attacks. To counter such adversary attacks, much effort has been devoted to empirical defense methods. However, such empirical defense methods are not guaranteed to be effective for adaptive attacks, which assume attacker is aware of defense strategy. Thus, certified defense for CBIR that theoretically guarantee robustness is needed. In this work, we propose certified defense for CBIR consisting of two components. First is verification algorithm to verify whether given inputs achieve alpha-epsilon robustness defined by us. Alpha-epsilon robustness guarantees that rank invariance against query and candidate attacks. Second is robust training to train feature extractor to increase the number of samples that satisfy alpha-epsilon robustness. Unfortunately, complete verification of alpha-epsilon robustness is computationally untractable. Thus, to recover tractability, we derive computational tractable sufficient conditions of alpha-epsilon robustness and evaluate them. The sufficient conditions are based on upper and lower bounds of distance against perturbations. The bounds can be evaluated by interval bound propagation algorithm, which obtains upper and lower bounds of model output through threefold propagations. We experimentally confirmed that the sufficient conditions are not always satisfied for all inputs when we use feature extractor trained by conventional metric learning. This is because the upper and lower bounds can be too loose to satisfy the sufficient conditions. So, we proposed new objective functions to train feature extractor that attain tighter evaluation of the upper and lower bounds of distance. One is training of general feature extractor without knowledge of query and candidate images. This is called tightly bounding training TBT. The other is fine-tuning of feature extractor to given candidate images. This is called fine-tuning candidates with tighter bounds FCTB. These objective functions increase the number of inputs that satisfy the sufficient conditions. We evaluate TBT and FCTB in terms of CBIR performance on clean images and certify robustness against query attack and candidate attack. This table shows results on MNIST dataset. We can see TBT and FCTB has less performance on clean images than other methods. However, TBT and FCTB achieve significantly higher certified robustness than other methods. Please see our proceedings for further details of this work. Thank you for your attention.